Welcome to this custom-tailored deep dive.
Hmm.
If you walk into a Michelin-starred restaurant, you can look right at the final dish on your table.
Right. It looks perfect.
Exactly. You
Hmm.
see the presentation, you can taste the ingredients,
Hmm.
the truffles, the wagyu, the perfectly reduced sauce. You experience the magic of it. But if you walk into your own kitchen the next day and you try to recreate that exact dish just by having tasted it, you are going to fail miserably.
Oh, absolutely. Because you're entirely missing the process.
Right. You don't have the recipe, you don't know the exact temperature of the oven or the sequence of the prep or the specific techniques the chef used behind closed kitchen doors.
Yeah, you're missing those hidden step-by-step instructions that actually turn those raw, everyday ingredients into something spectacular.
And for the past year or so, that is exactly how big tech has gatekept artificial intelligence. I mean, we can all taste the final dish, right? We use these incredible AI search agents that can scour the web and write reports for us.
Yeah, but the actual recipe for how to train an AI to do that, that's been locked in corporate vaults.
Until now. Today, we are looking at a groundbreaking new research paper titled OpenSeeker, Democratizing Frontier Search Agents by Fully Open Sourcing Training Data.
It's a huge deal.
It really is. It comes from a purely academic team at Shanghai Jiaotong University. And they didn't just build a world-class AI search agent to compete with the giants. They published the exact step-by-step recipe for how they did it.
They gave away the secret sauce.
Okay, let's unpack this because this feels like a massive shift in how AI is going to be built moving forward.
Oh, it's a seismic shift. And this matters so much for you listening because every time you use a search engine for deep research, or you ask an AI to prep you for a complex meeting by pulling data from across the web, you're relying on capabilities that are currently monopolized.
Right, they're completely walled off.
Exactly.
Mm-hmm.
We're talking about agents that can autonomously navigate the internet, reason through roadblocks, and use digital tools over dozens of steps. And right now, those ultra-smart deep search capabilities are proprietary models from giants like Google or OpenAI with their deep research.
They own the kitchen.
They own the kitchen, the ingredients, and the chefs.
But wait, haven't we had open source AI models for a while now? I mean, I can go online today and download a massive large language model right to my laptop.
Sure, yeah.
There are tons of open weight models out there, like Kimi or Minimax. So why is building a search agent suddenly hitting a brick wall? Why is this specific corporate data moat so impossible to cross?
What's fascinating here is that a model is truly only as good as the behavior it's trained to exhibit.
Okay.
Standard models like the massive LLMs you can download today, they are fundamentally just trained to predict the next word in a sequence of text.
Right, they just guess the most likely next word.
Exactly. They read billions of pages of the internet, and they become fantastic at pattern matching and generating human-sounding text. But a search agent needs to do something entirely different. It needs to learn a continuous loop of action.
A loop.
Yeah, we call it the reasoning tool call, tool response loop.
Meaning it has to actually, think about what it doesn't know, actively type a query into a search bar, read the results, and then think about what to do next based on what it just read.
Precisely. It has to navigate long horizons of actions.
Yeah.
If you just take a standard open source LLM and ask it to do deep research, but you haven't explicitly trained it on high quality data that demonstrates this very specific multi-step navigation, it just crashes and burns.
Just gives up.
Or worse, it will hallucinate, or it will search for the wrong thing, or it will just get stuck in an endless loop. Think of an open source LLM like a high-performance sports car with no steering wheel.
Oh, I like that.
You have this incredibly powerful engine, the reasoning capacity of the neural network. But you have literally no mechanism to steer it through the messy reality of the internet.
So the open weights models are just the engine.
Exactly. OpenSeeker is so groundbreaking because they are the first to open source the entire pipeline. They aren't just giving us the 30 billion parameter model.
Right.
They are handing over the 11.7 thousand incredibly high quality training samples, the exact steering wheel.
Wow. They gave us the training data. But that actually raises a huge question for me.
What's that?
Well, if I search, how long to boil an egg, that's just a single step. That doesn't teach an AI how to do deep, multi-step research.
No, it doesn't.
So where on earth did this academic team get 11,000 examples of perfect, multi-step, highly complex internet research? They couldn't just scrape normal, everyday web searches.
Definitely not. Normal web searches are way too simple.
Right. So they had to somehow invent questions so notoriously difficult that an AI is literally forced to learn how to search deeply just to survive the training.
And that brings us to their first massive technical hurdle. They had to artificially synthesize these training questions. The paper calls their method fact-grounded, scalable, controllable QA synthesis.
Okay. Wow, that is a mouthful.
It's heavy academic jargon, yeah.
Yeah.
But to translate that, they basically reverse engineered the entire concept of a trivia question using the real structure of the web.
I love this part of the paper. Let's break down how they build this perfect puzzle. Because if you just ask a standard AI to, write a hard question, it's probably going to hallucinate something that doesn't actually exist.
Oh, absolutely. It'll invent a fake historical event or a fake person.
And if you train your brand new search agent on fake facts, you're basically just teaching it to be a creative liar.
Exactly the problem. Hallucination is the absolute enemy of a reliable search agent. You need it to be strictly anchored in reality. So the researchers don't start with a question at all.
Wait, they don't?
No, they start with a massive web corpus, about 68 gigabytes of English web data and 9 gigabytes of Chinese data. And they just pick a random seed web page.
Okay, so like a starting point.
Yeah. Let's say it's a Wikipedia page about a specific obscure protein. From there, they perform what they call topological graph expansion.
Which means they literally just click the links on the page to see where they go, right?
Essentially, yes. They write a program to expand outward, following the hyperlinks from that initial protein page to gather a cluster of connected pages.
Like following a trail of breadcrumbs.
Exactly. Maybe a link goes to a specific research lab in Germany, and then a link from that lab goes to a scientist's biography, and a link from there goes to a patent filed in 1998.
Okay, I see where this is going.
They extract the central themes and pull out a dense entity subgraph. It's a literal map of real-world knowledge that is structurally linked together by the actual architecture of the internet.
So they have this web of true facts, but if they just generate a question based on those facts, like what patent did this specific German scientist file in 1998, the AI being trained might just do a simple keyword search.
Right, it would be too easy.
It might just look up the scientist's name, find the answer in one click, and learn absolutely nothing about complex reasoning.
Which completely defeats the purpose of teaching it multi-hop reasoning.
Yeah.
If the answer is one click away, the AI gets lazy.
Makes sense.
So the researchers introduce a brilliant intermediate step called entity obfuscation. They look at that map of facts, they take the specific concrete entities, the scientist's name, the name of the lab, the specific city, and they intentionally blur them out.
Blur them out how?
They replace those hard nouns with vague, descriptive references. So instead of Dr. Johannes Smith, the prompt becomes the lead author of the 1998 patent regarding protein X.
Oh, wow. It sounds exactly like designing a scavenger hunt for a genius.
It really does.
You take a real-world map, but you intentionally smudge all the street names. You tell them, go to the coffee shop next to the building where the mayor was born instead of just giving them the actual address. You're guaranteeing it's a hard puzzle because you built it backwards from the answer, but you are also strictly guaranteeing that a solution exists in the real world.
That is a perfect way to visualize it. This ensures absolute factual grounding. By anchoring the questions to the real topology of the web and forcing the AI to deduce the blurred entities one by one, they completely eliminate the risk of hallucination.
That's incredibly smart.
And because there are terabytes of web archives available, this method is infinitely scalable. They can generate endless, unique, highly complex puzzles.
But they don't just stop there, right?
No, they still don't just blindly trust the question they generated. They put it through a brutal quality control process called dual criteria verification. It uses a technique called rejection sampling.
Right, they generate a bunch of puzzles and throw out the garbage ones. So how do they decide what's garbage?
Criterion 1 is difficulty. They take the generated question and they give it to a strong existing AI model in what's called a closed book setting.
Meaning no internet access.
Exactly. No search tools, no internet. It has to rely purely on its internal memory. If the AI can answer the question correctly without searching, the question is immediately thrown out.
Because it's too easy.
Right. It doesn't force the AI to use tools, which is the whole point of the training.
That makes total sense. If I know the answer off the top of my head, I'm not going to bother opening a web browser. So you filter out anything that can be memorized. What's the second check?
Criterion 2 is solvability. This is the logical consistency check. They take the same question, but this time they give the AI an oracle setting.
An oracle setting.
Yeah, they basically say, here's the question, and here is the full unblurred map of facts we used to make it. Here are all the clues perfectly laid out.
So they give it the cheat sheet.
Exactly. If the AI looks at all the perfectly laid out clues and still cannot derive the correct answer, it means the reasoning path is broken.
Ah.
The wording is too vague, or the logic is just flawed. So they throw it out.
That is incredibly rigorous. So what survives this gauntlet is a data set of purely logical, factually grounded, mind-bendingly difficult questions that strictly require an AI to perform multi-step external searching.
Precisely.
Okay, so they've engineered the world's most difficult scavenger hunt. But handing a hard puzzle to an AI is kind of useless if the AI just gets overwhelmed and forgets the question while digging through the junk of the real internet. How do they stop it from drowning in ads and pop-ups?
That is the crux of their second major innovation. They call it denoise trajectory synthesis because, as we all know, the actual internet is incredibly messy.
Oh, it's a disaster.
Real web pages are full of irrelevant junk. You have sidebars, cookie banners, navigation menus, totally unrelated tangents.
Auto-playing videos.
Right.
Yeah.
And if an AI is doing web scale search, it has to ingest all of that raw HTML text.
And an AI only has so much short-term memory, right? The context window. If it reads 40 pages of junk, it's going to forget what it was originally looking for.
Exactly. The context window just gets bloated. This is a fundamental challenge in long-horizon tasks. If you are making 40 or 50 separate tool calls, searching, clicking, reading, going back, the raw HTML observations pile up so fast that the AI loses its train of thought.
So how did they fix it?
To solve this, the OpenSeeker researchers split the training process into two distinct phases. Think of it as a teacher AI and a student AI.
Oh, okay. Let's start with the teacher. Because what they do to help the teacher AI generate the golden path, like the perfect way to solve the puzzle, is so clever. They use a retrospective summarization mechanism.
Yes, when the teacher AI is generating the perfect step-by-step trajectory to solve that difficult scavenger hunt, the researchers wanted to make flawless decisions.
Right.
So they give it a pristine environment. At any given step, the teacher gets a clean, perfectly summarized history of all his past actions and findings. But crucially, it gets the raw, unedited text of only its most recent step.
So it has perfect, concise, long-term memory via the summaries, but it still gets to look closely at the immediate evidence right in front of its face.
Exactly.
It's not operating totally in the abstract. It still sees the specific web page it just clicked on.
Correct. The paper calls it the summarized history plus raw recent protocol. It works sort of like a rolling window of compression.
How does that work in practice?
Well, once the teacher AI reads that raw recent page, makes a decision, and clicks a new link, the system pauses. It goes back, takes that previous raw page, runs it through a summarizer to strip out all the ads and junk, and tucks that clean summary neatly into the history window.
Oh, that's brilliant.
Then it presents the brand new raw page. This allows the teacher to operate flawlessly for dozens of steps without ever getting overwhelmed by the noise of the internet. It generates expert-level reasoning and perfect tool calls. It maps the perfect road.
Okay, but here's where I get a little confused. If this clean, rolling summarization makes the teacher perform so incredibly well, why wouldn't they just build that into the final OpenSeeker model? Like, why not let the student use that exact same summarizer when you deploy it in the real world? It seems like they built a perfect pair of noise-canceling headphones and then literally refuse to let the student wear them.
If we connect this to the bigger picture of how AI is actually deployed, you'll see why that's impossible. Real-world deployment needs to be fast, and it needs to be computationally cheap.
Okay.
Running a secondary, highly capable summarization model at every single micro step of a 50-step search is incredibly slow. It doubles your compute costs. It introduces massive latency.
So it's just too expensive and slow for the real world.
Exactly.
Yeah.
You don't want an agent that relies on a crutch to filter noise. You want an agent that just naturally knows how to filter the noise instantly within its own neural network.
Oh, I see. So you have to teach it to ignore the noise intrinsically.
Exactly. And this is the most brilliant asymmetry in the entire paper. In the training phase, they take the beautiful golden reasoning steps and tool calls generated by the teacher.
The perfect route.
Yes. But when they feed this data to the student model to train it, they strip away all those clean summaries from the context.
Wow.
They force the student model to predict the teacher's perfect next move, but they make the student look at the raw, messy, incredibly noisy history of the actual web pages.
It's like teaching a pilot to fly.
How so?
The teacher AI gets to fly the route in a clear, sunny sky with perfect instruments. It logs exactly when to turn, when to climb, when to descend. But the student AI is put in a simulator during a hurricane.
I love that.
You give the student the chaotic, noisy radar screen of a storm, and you say, you still have to execute the exact same perfect turns the teacher made. By forcing the student to predict the perfect sunny day maneuvers while staring at a chaotic screen, its brain naturally builds an internal filter for the storm.
That is a phenomenal analogy. By forcing the student to predict optimal actions while literally drowning in raw data, the model implicitly internalizes the ability to denoise the context itself.
That makes total sense.
During training, the weights of the neural network adjust to mathematically ignore the ads, the sidebars, and the irrelevant text. It learns to find the needle in the haystack automatically without needing that slow summarization crutch in the real world.
That is incredible. They use the clean data to map the route, but they make the student run the route in the mud so it builds the muscle.
And the proof that this muscle building works is in the empirical results. Which brings us to the David versus Goliath aspect of this research, which is truly shocking.
Here's where it gets really interesting, because in the AI world, we are completely conditioned to believe that bigger is always better.
We really are.
We constantly hear about corporate models trained on tens of millions of data points using massive server farms that use as much electricity as a small town. But the OpenSeeker team trained their model on just 11.7 thousand synthesized samples.
Specifically, 10.3 thousand English samples and 1.4 thousand Chinese samples. It is a microscopic dataset by industry standards.
And they only did a single supervised fine-tuning run, just one pass. So instead of the traditional, wildly expensive method where an AI learns by trial and error over millions of attempts, which is called reinforcement learning, and it costs a fortune in computing power to simulate, they literally just showed this AI 11,000 perfect examples of how to behave once.
Exactly. No complex RL loops. Just here is the perfect behavior, copy it.
That is unheard of.
Well, due to resource constraints, as an academic team, they literally couldn't afford to run it multiple times or hyper-tune the parameters with expensive reinforcement algorithms.
They didn't have the big tech budget.
Right. Yet despite this shoestring budget, OpenSeeker achieved state-of-the-art performance across multiple rigorous industry benchmarks. We're talking BrowseComp, Xbench Deep Search, Wide Search.
Let's talk about the benchmark that really jumped out from the paper, BrowseComp ZH, which is the Chinese language benchmark. OpenSeeker scored a 48.4.
Which is staggering, because it actually beat Alibaba's Tongyi Deep Research model, which scored a 46.7.
Alibaba,
Wow.
one of the biggest tech conglomerates on the planet.
Yes. And Alibaba's Tongyi Deep Research didn't just use simple supervised fine-tuning. They used a massive, resource-heavy, multi-stage pipeline involving continual pre-training, SFT, and extensive reinforcement learning.
And OpenSeeker beat them with a mere 1.4 thousand Chinese data points.
Incredible.
How is that even mathematically possible? How does a model trained on 1,000 data points beat a model trained on a corporate-scale data set?
Yeah.
I mean, the paper also points out another model, Rethinking, which used 147,000 samples and scored an abysmal 13.8 on that same benchmark without RL.
Yeah.
Quality absolutely obliterated quantity here. It's like they fed this AI a Michelin star tasting menu of perfect bites, while the other models were force-fed a fast food buffet of hundreds of thousands of cheap data points.
It completely comes down to the density and difficulty of those 11,000 samples. When you look at the statistics of the OpenSeeker training data, the picture becomes clear. The Chinese dataset they synthesized averages a staggering 46.35 tool calls per trajectory.
Let's just pause on that and really think about what that means. 46 tool calls.
It's a lot.
That means the AI receives a prompt, decides what to search, reads a page, realizes it's a dead end, backs out, modifies the search query, finds a 30-page PDF, uses a tool to search within the PDF for a specific keyword, extracts a data table, does math on that table, realizes it needs more context, and searches again 46 separate times, just to answer a single question.
Exactly. It's exhaustive, deeply complex research. And the average token length for those trajectories, meaning the sheer amount of text the AI has to process to get from the start to the finish line, is 76.1 thousand tokens per sample.
Wow.
For comparison, the actual benchmark they are testing on, BrowseComp ZH, only averages about 27 tool calls and 15,000 tokens.
So the training data they engineered is actually exponentially harder, deeper, and more convoluted than the final exam they're being graded on.
Yes,
No wonder they aced it. They essentially trained for a marathon by running an ultramarathon at high altitude.
precisely. And this paper proves that you don't need a multi-billion-dollar supercomputer to create frontier-level AI behavior. You don't need a massive proprietary corporate data moat.
You just need better data.
If your data synthesis strategy is smart enough, if you aggressively ground it in reality using the topology of the web, mandate multi-hop reasoning by blurring the entities, and elegantly force the student to internalize the noise filter during training, you can achieve state-of-the-art intelligence on an academic budget.
So what does this all mean? The OpenSeeker team didn't just build a great search agent to show off at some conference. They published the blueprint.
You published every day.
They fully open source the question-answer pairs, the massive trajectory logs, the code, the denoising process, and the model weights. They are truly democratizing access to frontier intelligence.
And that's the real victory here.
Yeah. This matters to you because the tools you use for your daily research, for prepping for those massive meetings, or for doing your own deep learning are about to get exponentially better. They're going to become more accessible, open source, and crucially, they will no longer be permanently gatekept by a few massive tech corporations. The closed-door game is officially over.
And this raises an important question, something for everyone to really mull over as this technology unfolds.
What's that?
If a small academic team at Shanghai Jiaotong University can reverse engineer the web to teach an AI how to think, navigate, and search this deeply with just 11,000 synthesized examples, what happens next?
Right.
What happens when the global, fully open-source community takes this exact, proven method and scales it to millions of examples using the endless terabytes of web archives available?
It's a wild thought.
Are we looking at a future, perhaps very soon, where the world's most capable, tireless, frontier-level researcher doesn't live behind a paywall on a server farm in Silicon Valley, but lives entirely locally, running quietly on your own laptop?
It changes everything. You don't have to just look at the dish through the restaurant window anymore. You can finally cook it yourself. Thank you all for joining us on this custom-tailored deep dive. Keep questioning, keep exploring, and we'll see you next time.